I've seen some like cotton balls hanging.
All right. So limits. So infinity. Hey, maybe we should answer that question about Infinity Hotel.
Yeah,
we should.
And I forgot I was going to Google it, but I don't even know. I mean, yeah, whatever. If you did, I'll be interested to hear what it might have said. But there was, so you've got this hotel that has an infinite number of rooms, and it's full, right? Someone in every room. So, well, there's someone in every room, right? Go to room 100, there's somebody in it. Go to room 1 million, there's somebody in it. Go to room 10 million, there's somebody in it. Right? Any number you can think of, go to that room, there's somebody in it. So, right, we have to ignore the fact of how many, if there are infinite people. Yeah. Okay. Now, somebody comes to the front desk and wants a room. Can you give them a room?
Depends when they want to check in.
No, but they're all full.
It depends when they want to check in.
I want to say,
because what if someone's leaving? You know what
different than
I mean?
There's always going to be another one.
There's no, yeah, ignore check-in times, ignore somebody leaving, right?
What if it's like the husband of one?
Right? No, they want their own room. This person is coming and they want their own room. Nobody's in it.
Not possible to give an infinite number of people when you're out as a person. Wait, how can I be vendors?
Does it really matter?
They have their own.
What if it's
Yeah,
just
they're
a hotel
insignificant, so we just already have it.
Because full relates to like answers where it's not yes or no.
Well, but what I define as full is there's someone in every room. So you're right. They're all the numbers are whole numbers, right? All the room numbers are whole numbers. How many whole numbers are there? There's an infinite, right? Every room is a whole numbered room. You can come up, pick any whole number you want. There's a room and there's someone in it, right? So that's what it means in this problem to be full. What's that?
Like if there's an infinite amount of rooms, doesn't that mean that it's like increasing and therefore you can always add a person's
No, because it wouldn't have to increase at an increasing rate. It could be like natural log. It could increase, but it's not. This is a linear thing. Room 1, room 2, room 3, room 4. You know what I mean? So it's not about an increasing. It's not a derivative situation. So how about this? Let me couch it this way. So I think you're complicated. I mean, good stuff you're saying here, but I think we're overcomplicating it. So the question would be, if this person could get a room, how could they get to that room, and what room number would it be? Well, save the suspense. Here's how they would do it. They would get on their intercom, which of course would have to stretch a long ways to the infinite number of rooms, but would get on the intercom system or whatever they had, and they would ask everyone there to move to a room that was numbered one higher than the room they are currently in. Could they do that? Everybody's in a room that's got a number, a whole number on it. Could they pick up their stuff and move to a room that was one higher than the number they were in? Wouldn't there always be a room for every single one of them to go to? And what would happen after they made that move?
A new room would pop out of nowhere.
No, there wouldn't need to be a new room. At the very end, there is no end, right? It's infinity. Room number 1 would be open. Room number 1, I said whole number. They should be natural numbers because there wouldn't be a room 0. I guess if it was whole numbers, there would be a room 0. So room 0 would be open, whatever. The first room would now be open, right? So that person could go to that room. Okay? So, and then the way I remember it in college, the next question was, okay, now a baseball team comes, and I don't know what a baseball team did, but they needed 9 rooms. I guess 9 players. The player was that. Can they accommodate, so that it's full, can they accommodate 9 new rooms?
Yeah.
Everybody move to a room that's 9 higher than the one they're in now, right? Which they could do. There'd be a room for everybody, and there'd be 9 empty rooms now.
What about the person
Those
that's
people.
starving to death
towards the end, like the billions there. Hotel.
And they can't what?
They can't walk that far.
Well, they don't have to walk because at the Infinite Hotel they have a Star Trek like transporter, and they just transport them. You're right, that would get hard. And but they only had the room. You're right, getting to the room might have been hard, but they only got to go 9 more, right? So 9 more rooms wouldn't be that bad. But yeah, we'll say there's some transporter being that they could just transport themselves. Okay, but actually that's not even the difficult part of the question. So now you've got the idea there. Okay, now there's a big convention hits town. Of course, this hotel's already full, so maybe there's 2 conventions. This hotel is now still full, and another convention, I don't know, group of traveling salesmen, an infinite number of traveling salesmen have now shown up and want rooms. Can they fit them in?
No.
Yes. Yeah.
Undefined.
Well, you would think you could fit them in. Infinity plus infinity would be infinity, but the question is, how do they get to a room?
With their magic transport. Sorcery.
But you couldn't ask them to move to a room that's an infinite number bigger than the one they're in.
Tell them they can walk.
Right?
Do it one at a
So what we were doing before wouldn't work.
Okay,
So would there be a way to do it?
Check all the people out.
massive.
Tell them to
What's
go
that?
on the second floor. Tell
Any
them
ideas?
go to the second floor.
Yeah. The second floor is empty. No, it's not empty because it's full. The hotel's full.
But it's not full.
It is full. There's somebody in every room. Nobody? No ideas. You have to be able to tell them to go to a specific room. That's the only way. Like we said, go to one higher than the one you're in. Go to 1 9 higher than the one you're in. We need to have we need to open up an infinite number of rooms.
Why do people have to come in their rooms? Why can't the
Well, that's the only way it would work.
Because
There's no end, right? I mean, there's no end. You've got to open up rooms, so you've got to have the move because all the rooms are full.
And what does that person at the end go?
There is no end, number one. There's always a room 1 higher. There's always a room 1 higher than the one you're in. See, I mean, what you're bringing up is this, how difficult it is to grasp this concept of infinity, right? Because we keep wanting to talk about it in the end, and we keep wanting, right? But remember, there's always another number. You can always add 1. Whatever number room you're in, you can always add 1 to it. You can always add 9 to it. Okay, but now the problem is, and this is where this points out this concept that infinity is not a number. We cannot ask them to move to a room an infinite number beyond the one they're in. But there is an answer to this. There is a way to accommodate these infinite traveling salesmen.
Take 1 by 1.
Nobody's thinking of it yet? No?
This is like unrelated, like sort of.
Okay, well, okay, go ahead.
So would you say infinity is circular rather than linear then?
Yeah, although in a circular situation you would start repeating, you know what I mean, which doesn't have to happen. But, well, here's the answer. Here's the answer. You would ask everyone in the hotel to go to a room that is double the number of the room that they're in.
Oh.
So what does that mean?
Because
Room 1 would go to room 2, room 2 would go to room 4, room 3 would go to room 6, and what would happen?
They'd start opening up more.
What would open up? All the odd rooms would be open. Everybody there would now be in an even room. How many evens are there? An infinite, so they would all fit, right? And it would open up all the odd rooms, and how many odd rooms are there? Infinite, so they could all move to an odd.
I'm saying that also helps.
Okay? Yeah, now, you're right. It might be the last time these people stay there, because they keep having to move every time somebody comes, but,
I mean, you can
anyway.
check in anytime you like.
Okay, you can never leave. Yeah, that sounds familiar.
Would you say
All right.
infinity is the inverse of 0?
Okay, so let's start talking about these limit things. Now, Jordy just asked a question that is something interesting that I was going to bring up later, but since he asked, we'll talk about it now. I said, could you say that infinity is the inverse of zero? Now, I think from a kind of a common sense way of thinking, I say yes. From a purely technical way of saying no, just because, again, infinity is not a number. So those things, you know, it's kind of interesting. It's kind of related to something we've talked about in the math department. Mrs. Payne was asking me a question the other day about a log problem that she was a little bit stumped on in explaining, just because of it didn't work. She was following the rule and it wasn't working. And the problem was there was a negative base, and the log properties only work or only defined if you have a positive base. And the way I would explain it would be this. You guys know when you do square root of 12 and you break it apart into what? Well, 2 and 6, but you probably wouldn't do 2 and 6. Probably do 4 and 3, right? And because 4 is a perfect square, and that does that. Okay? Well, there's a rule of square roots that says square root of a times b is equal to square root of a times square root of b, right? Now, if you, and we usually don't pay attention to the fine print always in these things, and that was the issue she was having with this one. The fine print there says that this rule applies if a and b are both positive numbers. Because if you try that with two negative numbers, if you try negative square root of negative 3 and square root of negative 4, you may remember from Algebra 2, that's what? That's I square root of 3 times I square root of 4, right? Which would be I squared times square root of 12, and I squared is negative 1 square root of 12. But if you apply this rule, square root of negative 3 times square root of negative 4 would be square root of positive 12, and for some reason those two don't come out to be the same. Well, the reason they don't come out to be the same is this side is correct. This is incorrect. You cannot apply this rule that works here. You cannot apply that rule here, because this rule is only defined to be a rule if the a and the b are positive numbers. Okay, so when we talk about inverse numbers and stuff, Jordan, and yours, technically they have to be numbers, right? Infinity is not a number, so technically that doesn't work. But in practice and in just practical thought, I would say that's true, because when you write 1 over infinity equals 0, in practical thought, that's an okay statement. What you're saying is 1 divided by something really big is what? Really small. What you're really saying here is 1 divided by something that gets bigger and bigger and bigger is getting smaller and smaller and smaller. And the reverse of that would also be true. 1 divided by 0, of course, normally you would say, hey, that's undefined. But in the idea of limits, what we're saying here is 1 divided by something really small is really big. Now, what I often tell and it doesn't matter if this is a 1, it could be any constant of them. Now, so that's what you were kind of getting at, Jordan, right, as far as inverse, right? Now, what I typically will tell, like when I'm teaching freshmen and algebra, whatever, we talk about dividing by 0. Why can't you divide by 0? Why is that undefined? Okay, of course, there's the Siri thing. Do you guys ever do that on Siri, where they said the thing with Cookie Monster and stuff like that, which was kind of cool. But yeah, you have zero cookies and 0 friends, and, whatever. But why is divided by 0? Why is that undefined? Besides just that it doesn't make sense, like if you think about dividing up cookies. But what I usually say is this: 0 is the smallest number. So 1 divided by the smallest number should be the biggest number. And of course, there is no biggest number. So that's why what's the smallest absolute value was, right? So if you were going to take, because you take 1 divided by smaller and smaller numbers, they get bigger and bigger. So if you take 1 divided by the smallest number, you should get the biggest number. And there is no biggest number, so that's why you can't do it. Okay? But what we're saying here is 1 divided by smaller and smaller numbers is getting bigger and bigger and bigger. Infinity. Now, technically, like we say, we want to say does not exist there. when we're doing limits, but we can put infinity. All right, now, let's talk about what's happening here and what we've added here since yesterday. So let's kind of focus in now for the quiz and this kind of stuff. So in the black, we have the stuff we had before. Okay, in black, we have the stuff that we did back in chapter 2. If we have the limit as x approaches a number, you either are going to get a number, you just do substitution, you're going to get a number, means the limit exists, and that's your answer. It's where the cars would meet. Okay? You might get 0 over 0, we keep going, do some algebra to it. Maybe it exists, maybe it doesn't. If it does exist, you'll get a number eventually. Or you might end up getting this, which you could get when you direct substitute in the first place. You could get a number over 0, like 1 over 0 or 7 over 0 or whatever, which we know means infinity, like we were just talking about. But it also means vertical asymptote. That's what's happening. That's why it means infinity. When you get 7 over 0, 3 over 0 in a function, there's a vertical asymptote there. And on either side, you're going to have it going to infinity or negative infinity. So what we said yesterday, what I've added in the blue, is we want to then check on each side. We want to check A on the left, and we want to check A on the right. Now, the only possible things you're going to get are either infinity or negative infinity when you do that. When you check A on the left and A on the right in a vertical asymptote situation, you're not going to get numbers. Okay, you're not going to get a 2 and a 4, right? That would only happen in a piecewise function. And then we wouldn't be doing any of this stuff if we had a piecewise function. We'd just be looking at the graph, that kind of thing. So I'm talking about just normal type functions like what you saw in your homework, 9 through 21. Normal type functions, you're not going to get the cars coming in like at 2 different spots like this. It's either going to be going up or going down, infinity. Okay? All right, so we got that. So we added that yesterday to what we had in chapter 2, and then this is brand new. So you got limit problems where x approaches a number, and then you got limit problems where x can approach infinity. Now that's a different situation. We don't really plug in infinity, although we think about it kind of like we say what's happening as x gets really big. Graphically, that's way out at the right or way out at the left. What's the graph doing? So what that means is it probably involves a horizontal asymptote. When you're doing x approaching infinity, if you get a number, right, way out the left, if it's approaching some number, excuse me, way out the right, or way out the left, if it's approaching some number, that's a horizontal asymptote. Kind of different than this one. Here, the vertical asymptote is when you get does not exist, right? When you get a number over 0, you've got a vertical asymptote. Here, when you actually get a number answer, is when you have a horizontal asymptote at that number. Okay? If the limit doesn't exist, it's either because as you go way out to the right, the graph just goes up, 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 or goes down, down, down. It's got to do one of those things, right? It's got to go up, 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 down, 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 or it's got to approach some number. Those are the only things it can do out of infinity. Okay? Unless you had something weird like tangent, which goes up and then has vertical asymptote, and then goes up, and has vertical asymptote, and then goes up, right? But I wouldn't ask for one of those. Okay? So that's it. The question came up this morning. Well, how do you know if it doesn't exist? Well, if you don't get a number answer, right? A limit either has a number answer or it doesn't exist. It's one or the other, right? Look over here. We either get a number answer, we get 0 over 0, so we keep going, and then we get a number answer, or we get this. Doesn't exist. It's got to be one or the other. Get a number answer or it does not exist. If we get does not exist, we always have to go a little farther. We either check the left and the right, if it's one of these, or we say infinity or negative infinity if it's one of these. Okay? So again, our answer, we say does not exist, and we go a little farther. Okay? All right, that's a pretty good summary of that. So what are some examples of does not exist? Well, I just kind of went through that really. Example of does not exist is you're doing limit as x approaches a and you get like 7 over 0. That's an example of does not exist. Okay? And you check x approaches a from the left and you check x approaches a from the right, and you're either going to get infinity or negative infinity for those. Okay? And the other example of does not exist would be if you get a situation where you got limit as x goes to infinity, and you've got, infinity over, some number or something like that, where the top is getting way bigger than the bottom, either plus or minus, right? That's essentially what's happening there. Okay, those would be two really obvious examples of limit does not exist. Okay, and then of course you'd have your piecewise functions, limit. I don't know that that's going to be a big emphasis for us, but you get something like that. Limit does not exist in a graph, right? The cars don't meet. That's the example of does not exist we did a lot of earlier. Okay? All right. So let's run through the answers to this. Some of them will be real quick. Some of them will be take more thought maybe. So on this one, answer 0. So does that exist?
Yes.
Yeah, it's a number. 0's a number, right? So that's your answer. It would be a horizontal asymptote at the x-axis if you go way out. And again, it goes back to what Jordan said. It's kind of that inverse. You got 3 divided by infinity. That's 0. 3 divided by a really big number is a really small number getting smaller and smaller and going towards 0. Okay? What about this one?
0.
Also 0. As x gets really big, you do the square root. It makes it smaller, but it doesn't matter. As x gets really, really big, the square root of x is still getting big. Now, the graph of square root of x goes like this. It's a top half of a parabola laying sideways. So it doesn't get flat, but it doesn't go up real fast, but it's going up and up and up. So this is getting bigger and bigger and bigger down here. This is staying the same. It doesn't matter what number's up here. If it's just a number, it could be 1,000,000. This would still go to 0. Because the bottom would eventually get way bigger than 1,000,000. Okay? 0. On the quiz, you do not need to show any work on this one. It's no calculator, so the only way you're going to get -1/2 here is know what you're doing, right? So you do not have to show any work. But how did we describe this? We said that the 3
0 doesn't matter.
doesn't matter. As t gets really big, the 3 doesn't matter. This is going to get really big. The 5 is not going to matter. So it essentially becomes 2t over -4t. The t's would cancel, -1/2. But if you just remember that in your head, you say, hey, those will disappear, t's will cancel, it's -1/2. I don't need to see any work on that. Okay? Oh, look at that. It's the same exact problem. Except it's t approaches 0. So I like how your book did this, made you think about this. You really got to pay attention to this. Does the 3 matter here? Matters a lot, right? The 5, yes, it all matters because you were doing t approaches 0. So we substitute, and what do we get? 3/5. And what does that mean graphically? So if I was going to graph this, I don't know what it's going to do, but this graph is coming in and leaving, and those cars are meeting right there as t approaches 0, which would be on the y-axis. Those cars are meeting right there at 0.6 or 3/5. That's what's happening in that problem. This problem, what does that -1/2 mean? Horizontal asymptote. Way out at the end on this problem, this graph is going down towards -1/2. Might be coming from up above and leveling off, or might be, or below, or from above and leveling off. But at -1/2. Here it means those cars are coming in at 0 and they're meeting at 3/5. Okay? Important to understand, I think, the big picture here as well. Okay, what about this one?
Does not exist.
Does not exist. Infinity is the best answer right there. Okay? Because the top is getting big, 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 big. The bottom's getting big, 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 big. Top's getting big much faster. Now, we could also say, hey, the 1 doesn't matter. So what we talked about yesterday is it could just be this, which reduces to just this. So as x gets bigger and bigger, what does this do? It's x. It gets bigger and bigger. So this does not exist because it's not a number, right? A limit only exists if it's a number. Infinity is not a number. It's getting bigger and bigger. So this graph's just going up, 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 and away. Actually, what this does when we simplify this, I'm not going to get into this, but there's something called slant asymptotes or oblique asymptotes. What this x is, when I simplify that, y equals x is the oblique asymptote. So that's like, remember on that differential equation we had a problem that kind of did this kind of thing? This is what's happening in this problem, is you've got this thing and it's going and it's getting closer and closer to that slanted asymptote. So you have horizontal asymptotes, vertical asymptotes, and then this would be a slant asymptote. But as far as the limit goes, the limit does not exist because it's just going on and on. Okay? All right. What about this one?
1/2.
1/2. Because the 1 doesn't really matter. The 3 doesn't really matter. Cancel. 1/2. But again, it's because x is getting really, really big, so the high powers dominate, and that's what it ends up being. Okay? 15. 0. No explanation necessary. But what's happening is x goes way out to the right. This is going to be bouncing between -1 and 1. The bottom's getting really big, so it doesn't matter that this is -1 and 1. It's what we talked about. It's doing this, and it's kind of getting closer and closer to the x-axis, but from above and below. Kind of like a little sine curve that's squeezing down on the x-axis. Okay, what about 16? So it does not exist.
It's a complicated.
I think it's just negative infinity. Because of the 2. Because of the 2. Okay, let's talk about why that is. So when x gets really, really big negatively, -1,000,000, and you cube a negative, what happens? Stays negative. So you're going to get a really big negative on top. The bottom, what's cosine do as you go way out to the left? -1 to 1.
Yep.
Now what happens when you add that to 2? Because -1, the littlest it'll be is -1, and you add that to 2, that's 1. And the biggest it'll be is 1, you add that to 2, that's 3. So this is going to bounce back and forth between 1 and 3. So you're going to take these really big numbers, and you're going to divide them by numbers between 1 and 3, which are always positive, but they're small. So you take bigger and bigger numbers, divided by negative, divided by positive. Is it always going to be negative? And it's going to be getting bigger and bigger and bigger. So it does not exist, negative infinity. So that's one of those you just got to think your way through. What is happening to these values as x goes towards negative infinity? That's your thought process. Now I'm going to show you. Well, no, actually, we're going to learn a new rule today that we can use on some of these, not on this one. The only way to get that one is to think your way through it. Okay? All right. Well, I had a lot of questions on 17 and 18. The answer to this one is does not exist. Infinity. Now, as x gets really, really big, the top's getting bigger and bigger, the bottom's getting bigger and bigger. But this gets way bigger. Now, this would be a good thing to just put in your memory banks for all future uses. Exponential functions will grow way faster than power functions, always. And then likewise, when they flatten, like you take an exponential with a negative power, if it's flattening like Newton's law of cooling, it will flatten much faster than, say, a sideways parabola that's coming down, right? So it will flatten or go flat much faster in exponential, and it will grow much faster rate. I mean, just think about it. Put 100 in here for x. On your calculator, if you do 2 to 100 just on a TI-30, we did it this morning, you do 2 to the 100th power, it's like it puts it in scientific notation, like 1.2 times 10 to the 30th, compared to 100 squared, which is what, 10,000? I mean, so you got 10 to the 30th times 10 to the 4th. Okay? I mean, it's way bigger, and that's only putting in 100. And not only that, but even x squared, even if this was x to the 1,000th power, 2 to the x would eventually it would grow faster as x got bigger. Okay? So any power function is not going to grow as fast as an exponential. Now, where does that come into play? This is a really good example of an AP test problem where when we're doing areas later on, and it'll give you those two functions right there, and it'll ask you to find the area between the two kind of thing, and you graph them on your calculator and you see x squared looks like this, and you see 2 to the x looks like this, right? And you think they're talking about that area right there. But it turns out that if you zoom out and zoom out, what's going to happen eventually? Here's 2 to the x right here. What's going to happen eventually in 2 to the x? It's going to rise so fast, and what's going to happen to this x squared? They're going to cross again. But you'll never see it on your calculator unless you think to zoom out, zoom out, zoom out. But if you know going into the problem that, hey, 2 to the x is eventually going to outdo it and go way faster than x squared, you won't get tricked by that problem. And that's one of the reasons they ask you that problem, because they want you to know that. Matter of fact, if you go into that handout I gave at the very beginning of the year, I think when it talks about the topics, it specifically mentions knowing that magnitude of growth, it's called, that exponential functions grow at a much faster rate than power functions. It's a kind of a basic principle we want to make sure we grasp, okay? So once you've got that, then this is an easy problem. Then you look at that and you say, okay, the top's getting really big compared to the bottom, so this is just going to get bigger, bigger, bigger. So what if you had those flipped? 0, because you'd have big number on the bottom. So big number on the bottom means the fraction gets smaller and smaller. Okay? Well, this kind of relates to that. So now what happens if you put a negative into this power here? That's Newton's law of Coulomb. Right? It's coming down towards 0. Because you got 1 over 2 to the infinity. So this is getting really small and this is getting really big. What happens in a fraction if the top's small and the bottom's big? 0, and it gets there in a hurry, right? I mean, if you just have a constant here and the bottom getting big, it goes to 0. But if you got the top getting small and the bottom getting big, then it really goes to 0. Okay, but really not much work you can do to that. Okay, 19.
Infinity.
Definitely 0.
What's the back say?
I
I don't want to say because I don't want to know. What?
I think it said 0.
Think it said 0?
did it.
Okay, here's what you want to think of on these. This is a power function. Okay, but it's okay. This is a power function, but it's really the inverse of a power function. It's more of a cube root, right? So that means instead of growing like a parabola kind of thing, it's going to grow like this, right? And this is an inverse of e to the x. So remember when I talked about flattening? So e to the x is going to be way steeper than a power function. But ln x then is going to level off. Well, what's that mean about leveling off? It's going to level off much faster than a power function will level off. Because that's what a cube root, this one's going to level off. This is going to look a lot like ln x. If you graph these two, they're both going to look like inverses of a power function where they go up. But which one is going to level off faster? The ln x. So that means which one's getting bigger then? Faster. The power, right? So it's reversed, right? So ln x is leveling off, so they're both leveling off, but the power function is going to be going up more because it's not leveling off as fast. So therefore the bottom is going to be getting bigger compared to this. That's why it's 0. That's why it's 0. Now that's actually one, this new rule we're going to learn could help us on if you struggle with that. Okay, 20. Here's one you can actually, it's actually kind of a plug-in. This is kind of a do a limit inside of another function. So as x goes to infinity, really we're just going to work on this right here. So pi divided by a really big number is 0. But it's not exactly 0, but it's getting close to 0, right? So this is like asking, what is the sine function as its input gets close to 0? Well, you look at the sine function, and it's doing that, right? So as the inputs get close to 0, what do you got? 0. Yeah, it's fine to just say sine of 0 would be 0. That is okay. But again, just understand that's why. Okay? So that's 0. And 21. Plug in a 0. Sine of 0, 0. Sine of 0, 0. Okay? So nothing tricky there. Substitution. Okay, the last one I want you to do is this. Now the reason I want you to do this one, because I realized that none of them in the homework made us do this down here. And we did 2 of them yesterday. Guaranteed you're going to do one on the quiz. And I want you to do one of those. We've seen all of these, right? Probably not that one, but we've seen tons of those before. Okay, I want you to see one of those down there. So that's why 21's on here. So we plug in a 3 and we get, which means does not exist, but the question is what happens to 3 on the left and what happens to 3 on the right. Okay? So we put in 3 from the left to be 2.99999. 2.999 squared is basically 3 squared, which is 9 plus 5 is essentially 14. I don't really care. It's actually 13.999. It's going to be a little under, because when you take 2.99 squared, it's going to be a little under 9 plus 5. Whatever, I'd say just call it 14. Divided by 2.999 minus 3. Which is what? 14 positive divided by that? That's what we were looking for. We know for a fact that when we get 14 over 0, that means a vertical asymptote. That means infinity. Jordan said it earlier. Inverse, 14 divided by 0 is like infinity. Okay? We know we're going to get some infinities here. We just don't know if they're negative or positive. We got to check the left and the right. Okay? We know we've got this sort of situation with a vertical asymptote. So we just found out to the left of 3, it's going down like that. What about to the right of 3, which would be 3.01? That's going to be 14 over positive 0.001, which is positive infinity. So we know it's doing this. Okay? So those 2 circled, or those 3 circled things are what I want to see. Okay? This other stuff, it's good to write it out. I think you should probably write that out, but I'm probably not going to. You better have x approaches 3 from the left. I want to know 3 from the left is that 3 from the right. Whether you write down 2.999 and that stuff, I don't care. But I want to see approaching 3 from the left, approaching 3 from the right, and what they are. And then, of course, the main answer is does not exist. Okay? Obviously, the cars don't meet. Right? Okay. Here we go. L'Hopital's rule. So while you get your notes out,
Sounds pretty complicated.
it's, I don't know, is that French? It's got to be French, isn't it?
It sounds like almost Aztec, actually. Like,
Every now and then I get a little bit of trouble when I'm taking a lick. Every now and then I get a 0 for the numerator and the denominator. Every now and then I get a limit that's a fraction or some kind of indeterminate. Every now and then I get a bit of a ticker about, but then I think of all your rebuttals. That's why F1 bar to the That's why F1 bar to the
So you take the rate of change of the top and of the bottom, and there's a thing to rearrange. We're just going to compare them, and I know that you're making this strange, 'cause we take the limit again, and you find that you cannot define a limit, then you'll have to go repeat one more time. This all
Is that you, Mr. Clark?
I figured.
Once upon a time I was crying all night. Now I do my nothing but love.
There's nothing I can say. I have calculus in my
Mr. Gordon's an actual.
No, I don't think there is such a thing.
We're taking our test today.
But we could. There's a website, but I don't think.
I'm the star.
Oh wait, tour dates.
What?
UNO in April. Oh wait, they have a third edition. It's only $10.
Field trip.
Hey, look, there's a link to send us a gift.
Can we have like an fabulous field trip to go and see this?
God, I tried one time and they wouldn't let me.
Try again.
Is there any new ones? I think this is a new one. Good question. Whoops. Huh. I'll have to look into that. That is something I think we should do.
Look at that, that'd be so awesome.
That would be.
It would be an education.
Well, absolutely.
Oh, okay.
I don't know if people believe us that it was a real thing, but UNO in April. Okay, I'm gonna check that out.
We can't, I can't.
I would
Huh.
totally go.
I can follow it.
All right. Okay. So anyway, so here's L'Hopital's rule. L'Hopital's rule says if the limit as x approaches 0 or x approaches plus or minus infinity, it works for either. I'm sorry, not x approaches 0. X approaches a. Okay, if you have x approaches some number, or you have x approaches plus or minus infinity, of f of x over g of x. That's the key. It has to be a fraction. Okay? And if that equals 0 over 0 or infinity over infinity, and that could be plus or minus infinities, that doesn't matter. If it's one of those two situations, and again, like in the song, it said indeterminate, that's what those are. Now remember, we were mentioning this yesterday. 0 over 0 means you got small on top, small on the bottom. Now what happens? You'd think that'd be 1. Well, no, it's only 1 if they're getting small at the same rate. Right? Like 2x over 2x. That would be 1. And of course, rate of change is what? How do you measure rate of change? The derivative, right? It's a slope. Now 2x and 2x both have a slope of 2, so they have the constant rate. But if you had x squared over x squared, their derivatives, and that would still be 1, right? So it could be 1. But if they're getting small at different rates, then it kind of depends. So if the bottom is getting small faster, way faster than the top, it might go towards 0. Right? No, did I say it backwards? It'd be infinity, right? If the bottom's getting small faster, right? So in a fraction, the bottom small means the fraction's getting bigger, right? So it could be infinity, it could be 0, and it could be somewhere in between. Same thing with infinity over infinity. Top, bottom, both getting big. Well, if the top's getting big a lot faster than the bottom, then the whole fraction might be getting bigger. If the bottom's getting bigger a lot faster than the top, like we saw, 2 to the x and x squared, right? Then it could be infinity or 0. Or it could be somewhere in between, right? If those rates are proportional, right? The top's getting bigger 3 times faster than the bottom. Well, that'd be 3 over 1, right? That kind of thing. Okay, so you could just get a number. Well, so L'Hopital's rule is quite simple. Now, for those of you who still have to take the gateway, which, by the way, let's get doing that because now we're to 24 out of 30, right, if you pass it, okay? And there's a couple people. So if you haven't passed it yet, I think I put 0 in the grade book because I think the ones that haven't passed it yet haven't tried very many times yet. So it shows a 0 there now. Okay, so you gotta try quite a few number of times to get, where you can just say, I'll just take my best grade at this point. Okay, so make sure you're getting in to do that. Anyway, but so when I say that, it's easy to confuse this with the quotient rule because this is what we always wanted to do. Instead of the quotient rule, just say, hey, just do this, and here's what you can do. You can do the limit as x approaches a, or x approaches plus or minus infinity of f prime over g prime. In other words, just do the derivative of the top and the derivative of the bottom. Why? Because that's the rate of change. And so you can see what proportion that's in. Now it's possible.
Is that plus or minus?
Plus or minus infinity. Yeah. So if this is what you have, then I'm not saying this right, but the limit here, then you can just do that, and that'll give you your answer, L, called L for the limit. Now, it's possible that you still get infinity over infinity or 0 over 0. Then do it again. Then do it again. Okay? And it's possible the limit still doesn't exist, or it's possible you get a circular thing where it's always going to be infinity over infinity, and then you might have to do it a different way, or think your way through it like we said. Now, again, keep in mind, this doesn't work on all fractions. It only works when you have this. Okay, it only works when you have this. Sometimes it's helpful. Sometimes it's probably just as easy to do what we did. So it's just a tool that you can use. But there are times it might be quite helpful. But we just got to do a 9 through 21 and didn't use it at all, right? And we were able to come up with all of them. Okay, so now let's go back and look at some of those. So let's see, first of all, which ones could we do it on? Could you do L'Hopital's rule on this? This is 3 over, plug in infinity. This is 3 over infinity. Does that meet the criteria? The criteria is it's got to be 0 over 0 or infinity over infinity. This is not one of those. L'Hopital's rule doesn't have anything to do here. Okay? How about this one? No. So again, many of the times, you're just going to work them the way we just did them before. This is just an additional tool that you can use in certain situations. Okay? What about this one? As t gets really big, what's happening to the top? It's getting big. Infinity. What's happening to the bottom?
It's getting smaller.
Well, it's getting big. Negative. So this is infinity over negative infinity. Can we use L'Hopital's rule?
Yes.
Yes. The plus minus part of it doesn't matter. So we can use L'Hopital's rule. What's the derivative of the top? 2. What's the derivative of the bottom? Right? That's L'Hopital's rule. Okay? That's L'Hopital's rule. Because what's happening, again, this makes sense because what we found here is that the bottom is twice as big as the top all the time. As t gets bigger and bigger, the bottom is always twice as big as the top, which would make a fraction of 1/2. Okay? But that's rate of change. When we talk about twice as big, that's measuring its rate of change. Okay? What about this one?
No.
We plugged in a 0, what did we get?
2 over 9.
No. We just got 3/5. We plugged in a 0, we got 3 over 5. That was our answer. So L'Hopital's rule?
No.
Nothing, right? Doesn't work. Okay? This one.
Yes.
Infinity, as x gets really big, what's the top? Infinity. What's the bottom? Infinity. This is infinity over infinity. L'Hopital's rule work?
Yep.
Yes. So we do the derivative of the top,
2x.
2x over 1. Now we put in infinity. What do you get? Infinity over 1, which is infinity, which of course is what we have. Does not exist. Okay? Now, how did we think about it in the blue? We thought about it as the top's getting big and the bottom's getting big. Actually, we said the 1 doesn't matter. We reduced. We got this. That worked fine. Still will work fine. Just say the top's getting way bigger than the bottom. It's going to infinity. But this new thing would work too. Okay? X gets big. What's the top? Getting big. Infinity. Infinity. This is infinity over infinity. That fits L'Hopital's rule, so we can do the derivative of the top.
2x over x.
Or you could do it again. Yeah, you could reduce it. Or you could say, okay, that's still infinity over infinity. So do the derivative again. Derivative 2x is 2. Derivative 4x is 4. 2 over 4, 1/2. So you could just do it again. Right? X gets big. What's the top? -1 to 1. Bottom, infinity. Is that L'Hopital's rule? No. It's not 0 over 0, infinity over infinity, so we have to think it through the way we did here. L'Hopital's rule? No, that was infinity over 1 to 3. Okay?
Yes.
This is L'Hopital's rules. X gets big, that's getting big, bottom's getting big. So we can do the derivative. What's the derivative of 2 to the x? Over. Now, as x gets big, still getting big, still getting big. So it's still infinity over infinity. So do it again. 2 to the x. Now, ln 2 is just a number, so it's just going to hang out there. 2 to the x.
What about the quotient?
Hang on a minute. What's the derivative of 2x? 2. Now what do you got? As x goes to infinity, this is going to infinity divided by 2.
Still got one.
That's just infinity. No, don't keep going. It's infinity over 2. Right? Infinity over 2 is just infinity. Right? So L'Hopital's rule worked. We did it twice. So he said, what about the quotient rule? This is what the warning I was given about people doing the gateway test. We're not saying do the derivative of this fraction, are we? That's all we're saying. If we were going to do the derivative of the fraction, yes, we have to do a quotient rule. But that's not what we're doing. What we're doing is measuring the rate that the top is changing and the rate that the bottom is changing so that we can compare them, right? That's the whole idea. Which is getting big faster? That's the question. So L'Hopital's rule says, well, if you want to know the rate of the bottom compared to the rate of the top, do the derivative of the top, do the derivative of the bottom, and compare it. Right? That's what L'Hopital's rule is doing. So that's why we can get away with this. Do the derivative of the top, do the derivative of the bottom. Because we're not doing the derivative of the fraction. We're doing the rate of change of each of those separately to measure them. So they're two different, totally different things. Okay? All right. This was 0, remember? 2 to the negative infinity is getting smaller and smaller and smaller. And this was infinity. So 0 over infinity. Is that a L'Hopital's rule? No. So we would just think right through it. It's a 0. Okay? This is the one where L'Hopital's rule could really help you if you weren't sure about what was happening here. Because ln x, the graph of ln x does this. Gets bigger and bigger. X to the 2/3 is very much the same thing. This is x to the 2/3. Okay? Looks like that. Okay, kind of comes into the curve, kind of goes out of the curve, but it's very similar. It's like a cube root kind of a thing, like a square root. They all have that same kind of look. Okay, the roots. So they're both, this is infinity over infinity. They're both growing slowly, okay, but we talked about that. So we can do this. So what's the derivative of ln x? What's the derivative of x to the 2/3? Okay? Now, as x gets really big, what's this doing? Going towards 0. This would be 2 over 3x to the 1/3. As x gets really big, what's happening to that? also going to 0. So what do we got? We got 0 over 0. Now what's going to happen is this is going to keep continuing to do this, right? But eventually you're going to see that this would be x squared and whatever. So this is a tough one because your L'Hopital's rule just keep going, keep going, keep going. And you're going to keep getting 0 over 0, 0 over 0, 0 over 0. And at some point you got to stop and say, okay, which one is getting small, faster, larger, and all that stuff. Okay? So, God, I hope those aren't all calculus drops. All right. So, we've got at some point you got to think, hey, this is smaller than the bottom, and that's why it goes to 0. So that's a tricky one. Okay, this is not a L'Hopital's rule. We just plugged in, and this one we just plugged in. Okay, let's talk about a couple. Okay, so indeterminate forms. This would be good to put in your notes down. Okay. So indeterminate forms. 0 over 0 obviously is an indeterminate form. Infinity over infinity is an indeterminate form. Those are the two that we really think about the most. Okay? The one that's tricky is the one where we get 0 times infinity. Okay? That doesn't fit L'Hopital's rule because it's not a fraction. Okay? But it's indeterminate. And I was saying this earlier. You've got something getting small times something getting big. Okay? Now, the simplest example I can think of is related to number 17 and 18. 2 to the negative x, now I'm talking about as x goes to infinity now. What happens to 2 to the negative x? Gets small. Times x squared. That gets big. So what you have is a 0 times infinity. The question is the small one getting small faster or slower than the big one's getting big? Who's going to win this tug of war? The exponential in this case is going to get small. It's going to level way faster than the x squared is going to get big. So the 2 to the negative x is going to win. So in this case, it's going to be 0. If the bigger one wins, it could be infinity. And if there's kind of this back and forth, then it might end up being 1/2 or whatever. But the question is, how do you know that? Well, if you think about this, a pretty easy way to rewrite, and here's where L'Hopital's rule is going to come in. How can I rewrite 2 to the negative x? Couldn't I put it on the bottom and turn this into that?
Yeah.
And now I've taken my 0 times infinity and turned it into infinity over infinity, and now I can do L'Hopital's rule. So the lesson from that is that a 0 times infinity can always be turned into one of those two right there, because of what Jordan said earlier today, is that 0 and infinity are like reciprocals of one another. So you could take the 0 and flip it, and it becomes 1 over infinity. So you get infinity over infinity, or you take the infinity and flip it, and it becomes 1 over 0. And so you get 0 over 0. So anytime you have a 0 times infinity, you can do some algebra magic to flip, and you can turn it into one of those first two, and then L'Hopital's rule can work. So let's finish up here by doing a couple examples of that situation. Okay, here's an example right here. So we got x going to infinity. So this part's going to infinity. And what about e to the negative x? As x gets big, that's going towards small. E to the negative x is this right here. Right? Because it's 1 over e to the x. So it's 1 over something really big, which is really small. So we have an infinity times 0. So how could we rewrite this? X over e to the x. Now what do we have as x gets really big? Now I have an infinity over infinity. Now I can use L'Hopital's rule. Now, I don't think you need L'Hopital's rule. Can you see the answer already?
Yeah.
It's what?
0.
It's 0. Because the bottom is going to get big way faster than the top. So when the bottom gets way big, the fraction goes to 0. So I don't think you need L'Hopital's rule here. Just learn what we did, do what we did yesterday. It's 0. But if you want to do L'Hopital's rule, derivative of the top is 1, derivative of the bottom is that. Now as x goes to infinity, clearly it's 1 over infinity, which is 0. So L'Hopital's rule can apply, but not. And again, all the way back here, you could have said, okay, who's going to win this battle? E to the negative x is winning this battle. It's going to get smaller way faster than this is getting big, so this is going to go to 0. So you could have done it even back then. Okay? Now, if we want to talk about one that's going to come out to be a number, that it would be pretty obvious most of the time. It would be like having a 2x squared times an x to the negative 2. This would be going to infinity, this would be going to 0. Of course, we know by algebra that's just 2x squared over x squared, which would end up being just 2, right? I mean, so when we talk about, sometimes you can get this battle and it ends up being somewhere in the middle where you just get a number. Well, usually it's because of something like that. But if you've got a power versus an exponential, it's either going to be 0 or infinity off. Okay? All right. Let's do this one. Last one, I think. Okay? X squared times ln x. So as x approaches 0 from the right. Now, why do you suppose they put from the right there? What doesn't exist? Well, the ln. It's not because 0, but you can't put a negative into ln. So normally when you do a limit as x approaches 0, you got to look on both sides, right? So you'd have to look at ln from the left of 0. Well, there is no left of 0 for natural law, right? So it only makes sense to do from the right. That's why it is. Okay, so it's not like we have to do anything different here. But as x gets really small, this is getting small here. And what's happening to natural law? See, this is where you need to know the natural log graph, isn't it? As you approach 0 from the right, what's this doing? Bigger, negative. It's negative infinity. Right? So the answer I'm looking for is negative infinity. Okay? So this is a 0 times infinity situation. Okay? So the question is, how do we which one's going to win? Well, I think we might have a feeling, but let's rewrite it so we can do L'Hopital's rule. Okay? So somehow I want to get one of those flipped to the bottom. Now it's easy here, the negative power, boom, just flip it down. But it's not quite as obvious here. So what do you think? I think I would put the x squared down at the bottom. Right? I can't just move the ln x down. I'd have to move it down as a... I mean, if I wanted to write this as a fraction and keep the x squared on top, what would I write on the bottom? It'd be 1 over ln x, right? Or ln x quantity to the negative 1, right? Which I think would be kind of a messy derivative to do, right? So if I'm going to do L'Hopital's rule. So I think I'd rather move the x down. So this would be ln x stay on top, and then what on the bottom? X to the negative 2, 1 over x squared, or just x to the negative 2, right? Now what I have is an infinity, and then what about this? What's 1 over x squared as x approaches 0? As x approaches 0, the bottom's getting small, so what's this fraction?
0.
No, come on, not 0, 0, there's a 1. As the bottom gets small, what happens to a fraction? Gets big, right? When the bottom gets small, the fraction gets big, okay? So when the bottom is 1 over x squared, as we approach 0, that's going to infinity. So this is an infinity over infinity, so L'Hopital's rule works. So derivative of the top, 1 over x. Derivative of the bottom,
Negative 2x.
so that'd be 1 over x and negative 2 over x cubed, right? Now I think it would be smart to write that as x to the negative 1 and negative 2x to the negative 3. Because isn't there some algebra I can do to that? What? And be careful, yeah, okay, right. Kind of weird canceling with negative powers though. Tell me what it's going to be.
X squared on
x to the negative second. Yeah, see, here's what I do is subtract the powers. Or flip them and then cancel.
Yeah, just flip it.
Just flip them and then cancel. So now what about this negative 2? Does it flip? No, that stays. So let's move the x cubed up to the top. And let's move the x down to the bottom. Okay, so be careful with your canceling when you got negative powers because you could really screw that up. Okay? Or just subtract it. Negative 1 subtract negative 3 is 2. Right? So it's x squared. But anyway, so we can see what? We're going to get x squared. Now as x goes to 0, measure 0. 0 divided by negative 2. 0 divided by negative 2 is 0. Okay? So now, where we had the difficulty there, so the answer is 0. Right? So the x squared won. Right? Now, where did we have trouble with that? Well, we had a little trouble knowing which one to flip down. It was pretty obvious on this one. Pretty obvious on this one. Right? So a lot of times it will be obvious. Okay? This one wasn't quite as obvious, so I chose to make that one because I knew I was going to do L'Hopital's rule and I wanted to do the derivative easier, so I knew this would be easier. But once we got to here, it's just algebra. You got to make sure, once you do L'Hopital's rule, then a lot of times there's some algebra you can do to just simplify and make life easy. Okay, and then what do? You go back and you plug this in and you try. Okay? All right. So homework is those problems right there. I'll let you have the rest of the time here to work. Again, the only thing we've added today, mostly it's been about reviewing what we did yesterday. The only thing we've added today is L'Hopital's rule, which is just one tool to use, but it's very specific. It only works if you have 0 over 0 or infinity over infinity, those indeterminate forms, or if you have 0 times infinity, and you can flip one of them to get the 0 over 0, infinity over infinity. Then you do the derivative of the top, derivative of the bottom, and then try to do the derivative again. So it's just one tool, but sometimes you're better off just doing what we did yesterday, and sometimes you can't use L'Hopital's rule, so don't try to use it when you can't. That's probably the biggest problem people have with L'Hopital's rules. They try using it when it's not even supposed to be used. Okay? All right. So we'll do that tomorrow, or do that for tomorrow. Tomorrow we will kind of go over it. What's that? Oh, multiples of 4. Now, to be honest, it wouldn't hurt you to do the whole batch of them between 56 and 80. It's just a whole bunch of limit problems. Basically what I meant by multiples of 4 is just you need to do some and you need as much practice as possible. So it kind of goes back to the top of the page where it says the minimum problems to do, right? So you really should be able to do any of those limit problems on 56 through 80. Let me look at that page again just to double check here. Yeah, on 56 through 80, really, you should be able to do any of those, so it's just a good chance to get extra practice. So if you would rather do a bunch of the odd ones, so you can check them back. Now remember, you got your calculators. Your calculators will do limits for you. Kind of like checking your derivative problems. It's under that same place where we do limits, or derivatives is the limit key. So you can always check them there. Okay? So tomorrow we'll revisit this limit stuff again, and then we'll review the slope field stuff. Practice in Newton's law of cooling. I'll give you one of those to do for homework tomorrow, and then quiz Thursday. And work time to plan your calculus skills.
I think we're gonna take one from.
Yes. One of those songs. Oh, there you go.
Do they have any Christmas ones?
I don't think so.
So is that cool? They talked about.
What's that?
Talking about like the power versus the exponential, and how it works the opposite. Will that always be true? Where like the power will go down faster than just
will flatten. The exponential will flatten faster than the power will.
The power will grow.
The exponential will grow.
It'll grow and
Fast. Right. Because what it is,
So yeah, that makes sense.
Yeah, because they're inverse. When it flattens, it's an inverse, so that means it's a lot steeper here. So when it flattens, it's a lot more horizontal. This way it's a lot more vertical, this way it's a lot more horizontal.
Well, like the thing I was talking about was like with the L and
That's gonna be still
the X to the 2/3. We said that one.
Right, but I said the 2/3 would, yes. 2/3 is not a power law. Okay, that's an inverse. So we said what?
That the 2/3 would be the L.
Okay, but that's in getting big.